Welcome to the captivating world of planetary migration. Today, we're embarking on an extraordinary journey to explore how planets, formed from swirling clouds of gas and dust, traverse the cosmos to find new orbits. This dynamic process not only reshapes the structure of solar systems, but also plays a crucial role in determining the potential for life on planets like ours. So, prepare for an adventure as we delve into the secrets behind planetary migration. Planetary migration refers to the phenomenon where planets change their orbits over time, often moving far from their original positions within a protoplanetary disk. Imagine a bustling marketplace where each vendor adjusts their stall for optimal visibility and sales. In a similar way, planets can shift their orbits due to gravitational interactions with surrounding material, other planets, and the central star of their system. This process unfolds over millions of years and can significantly impact the architecture of a solar system. For instance, migration can influence the arrangement of planets, their sizes, and even their potential to host life. It raises fascinating questions about how solar systems evolve and the diverse environments that can arise from these migrations. Most planets originate in a protoplanetary disk, a dense, rotating cloud of gas and dust surrounding a young star. As solid particles collide and stick together, they create planetesimals, small building blocks of planets. These planetesimals continue to collide, merge, and grow, forming larger bodies known as protoplanets. As these protoplanets form, they begin to interact gravitationally with the gas and dust around them. This interaction is crucial for understanding planetary migration. There are two primary types of migration that scientists focus on: Type 1 migration, associated with smaller planets, and Type 2 migration, linked to larger gas giants. Exploring these two types provides valuable insights into the dynamics of planetary systems and their evolution. Type 1 migration primarily involves smaller planets, such as Earth-sized or super-Earths. As these planets grow and gain mass, they exert a gravitational influence on the surrounding gas in the protoplanetary disk. This interaction creates pressure differences within the disk. Gas flows toward the planet, which can lead to a significant inward or outward migration. Inward migration is particularly noteworthy. A small planet that begins in a stable orbit can spiral inward over millions of years, potentially ending up in a hostile environment close to its star. Here, intense radiation and heat could strip away its atmosphere and render it inhospitable for life. For example, consider planets in systems like TRAPPIST-1, where several small, rocky planets reside in close orbits. Understanding their potential migration paths is crucial for assessing their habitability. Type 2 migration involves larger gas giants like Jupiter and Saturn. These massive planets have strong gravitational fields that can clear a path through the protoplanetary disk, creating a gap around them. As the disk material gradually dissipates, driven by factors like stellar radiation and interactions with other bodies, the planet itself slowly drifts inward along with its created gap. This process is significantly slower than Type 1 migration, often taking tens of millions of years. During this time, the gravitational interactions can lead to complex orbital dynamics, influencing not just the gas giants but also smaller planets and bodies in the system. For example, the inward migration of a gas giant can destabilize the orbits of smaller, rocky planets, potentially causing some to collide or be ejected from the system entirely, as we might speculate happened in the early history of our solar system. The implications of planetary migration are profound and far-reaching. This process helps explain many of the surprising configurations we observe in different solar systems. For instance, many exoplanets, planets located outside our solar system, have been discovered in close orbits to their stars, leading to the classification of hot Jupiters. These gas giants, found in extreme proximity to their stars, exhibit temperatures much higher than what we would expect based on our solar system's layout. Migration theory provides insight into how these planets could end up in such tight orbits after initially forming farther away. Additionally, migration impacts the habitability of smaller, rocky planets. If a gas giant migrates too close to its star, it may disrupt the orbits of nearby smaller planets, possibly flinging them into the star or ejecting them into the cold, dark void of space. This disruption could prevent stable environments that are essential for the emergence and sustenance of life, emphasizing the intricate interplay between migration and habitability. To support the theory of planetary migration, scientists analyze an extensive body of data regarding exoplanets. Thanks to advancements in telescope technology, astronomers have identified thousands of exoplanets, many of which reside in unexpected orbits. These observations strongly suggest that migration is a widespread phenomenon across the galaxy. For example, many gas giants are found in orbits much closer to their stars than we would expect based solely on our solar system structure. This discrepancy has led to significant interest in understanding the mechanisms of migration. Additionally, computer simulations of protoplanetary disks have been instrumental in providing valuable insights into how these migration processes unfold. These simulations allow researchers to visualize the interactions and movements of forming planets as they evolve, offering a clearer picture of the migration dynamics at play. To deepen our understanding of planetary migration, scientists employ various theoretical models and computer simulations. These tools allow researchers to test hypotheses about how planets interact with their surroundings over time. By varying parameters such as planet mass, disk density, and orbital distances, scientists can explore a wide range of possible scenarios. For example, simulations have shown that even small changes in the initial conditions of a protoplanetary disk can lead to dramatically different outcomes for the planetary system. Researchers have utilized these models to study the formation of our solar system, exploring how early interactions between Jupiter and Saturn may have led to the current arrangement of planets. This ability to model various migration pathways not only aids in predicting the likelihood of finding habitable planets in different solar systems, but also enhances our understanding of how solar systems evolve. The study of planetary migration also carries significant implications for the search for extraterrestrial life. Understanding the migration paths of planets can inform us about their potential habitability. For example, if a gas giant migrates inward, it could affect the conditions on nearby rocky planets, altering their climates and environments. Some studies suggest that a planet's position in the habitable zone, the region around a star where conditions might be just right for liquid water, can change as larger planets migrate. This highlights the importance of understanding migration when considering the potential for life beyond Earth. If gas giants were to disrupt the orbits of terrestrial planets, it might result in environments too extreme for life to thrive, emphasizing how interconnected the fates of planets can be. Planetary migration is a vital concept that enriches our understanding of not only our own solar system, but also the countless others scattered throughout the galaxy. It reveals that the cosmos is a dynamic, ever-changing environment, constantly reshaping itself in ways we are still uncovering.